Today we're going to talk about one of the weirdest concepts, I think, in all of mechanics. I'm going to take this bowling ball. No. I'm going to take this hovercraft, turn it on, and what I want the people in the front... Oops. I'm going to take this hovercraft and I'm going to run it by the people in the front row, and the people in the back row, I want you to watch the heads of the people in the front row. Ready? Go. So people in the back row, what did you notice about the heads of the people in the front row? Were you watching their heads?
Yes.
Their heads turned. Why? Why did their heads turn? To keep track, right? Wouldn't you agree that they had to turn their heads or their eyes or something because the angle from them to the hovercraft was always changing, or at least was changing. So the question I have is, does the hovercraft have angular momentum? Yeah, so very weird. It's a very weird thing. It turns out that a particle traveling in a straight line does have angular velocity. Does have angular velocity. Why does it have angular velocity if it's traveling in a straight line? Because from the perspective of the person who's watching it, they have to turn their head to see it. So, if that person who's watching it, James, who's in the front row, has to turn their head at 0.5 radians per second to track the hovercraft as it goes by him, what is the angular velocity of the hovercraft with respect to James's head? 0.5 radians per second. Oh, this is interesting. What about Dino, who's sitting one row behind James, tracking the hovercraft? He would, if the hovercraft is this far away from James, and James sees it at 0.5 radians per second, and Dino's twice as far away, what do you suppose Dino might see it as? 0.25 radians per second? Just during that time? Does that make sense? So it really depends on where your axis of rotation is as far as how much angular velocity the particle has as it goes by.
So in this case, is the radius changing?
Ah, now that's an interesting question. When is the angular velocity of the particle the highest as it goes by your head? When it's right close to you, right? When it's right close to you, the angular velocity is the highest because that's when you have to move your head the fastest to track it. Got it? So just because a particle is moving in a straight line and not spinning, it can have angular velocity if you're watching it, because it's going to have angular velocity with respect to your head as your head turns. Got it? Now, interesting thing, as that hovercraft keeps on moving, keeps on going this way, gets farther and farther and farther away from James's head, what happens to its angular velocity? It decreases. How come? Yeah, you have to turn less fast, right? Turn slower as you get farther away. And the limit as it approaches infinity, how fast is your head turning? 0. Right? Good? All right, so that's kind of an interesting effect. The fastest, and Hassan just mentioned this, the fastest angular velocity is when you're extremely close because the R is the smallest, right? But as you get farther and farther away, like Hassan said, R gets bigger, therefore the angular velocity gets less and less and less. Sound good? All right. This idea is wacky, but true. All right.
So
Now.
as the car gets farther and farther away, your angular velocity is going to approach zero.
Right. Now, raise your hand if you've heard of the law of conservation of momentum. What's the law of conservation of momentum say? Say that again. Momentum, total momentum of a system before equals the total momentum of a system after. Okay. Or you could say the angular momentum of a system, sorry, the momentum of a system is constant, right? Just as long as you don't push on it. So if we think about this, I'm going to move my hovercraft right here across the table. Is its momentum constant just as long as I don't push it?
Yes.
Absolutely. How do I know?
Because it's not.
It's going in a straight line.
Its velocity is not changing.
Same speed, straight line means constant velocity, and
The mass is.
the mass is constant. So just as long as you don't push on it, momentum is conserved, meaning momentum stays constant the whole time. Does conservation of momentum work for angular momentum?
Yeah. It is.
What is angular momentum?
Momentum inertia takes up the velocity.
Okay, what was linear momentum?
Mass times velocity.
M times v, right?
Yeah.
So angular would be
M.
I times omega. Right. Is that quantity conserved? Oy. Okay. Well, we first got to define what angular momentum is. Well, it would be I omega, right? But does a particle have an I? Huh? Wait, I thought I was just for solid objects. Wait a second. Do particles have I? If you have a moving particle, how do you figure out the I of a particle? mr squared, right? What's r?
Distance from the axis.
Distance from the axis. So distance of the hovercraft from James's head would be r. Right? Because we did that before.
Yeah.
The particle would have an I value. And can the particle have an omega value?
Yes.
Which would be what?
How fast the head is turning.
V. Oh, it'd be how fast your head is turning, right? Okay. So mr squared times how fast James's head is turning. Okay, so here we go. Yes, a particle can have angular momentum. Wait a second. Oh, we just did the definition of angular momentum for a solid object, but for a particle, wasn't momentum m times v?
Yeah.
Yeah, it was. Well, angular momentum of a particle is actually r cross p. What's p? Regular momentum. So r, the radius vector cross product. You guys remember what that is?
Yeah.
Regular momentum. Right. But r cross p is just a fancy way of saying what? RMV sine theta. Because remember, the cross product becomes a sine theta? Right. Okay. What's L?
Is that the sign for?
Guess what letter we use for angular momentum?
L.
L. Why do we use L?
Because that's what somebody decided.
Oh, I think it's like a name.
I have absolutely no idea. Got it?
Punctured F and M was taken.
Right. M was taken. That's why. I have no idea. Oh, why is, question. Why does L have an arrow on top of it?
Vector.
Because momentum's a vector quantity.
Because angular momentum's a vector quantity too. Because R cross P makes a vector. Okay, so R. R is the distance from James's head to the hovercraft. V is how fast the hovercraft is moving. What's sine theta?
The angle.
Angle between R and V. All right. So when is angular momentum at a maximum?
When R and V are perpendicular.
R and V are perpendicular. Yeah, sorry, I should have asked what angle would produce the maximum. Yeah, 90 degrees. 90 degrees. Okay, good. So, I prematurely asked that question. Never mind, I didn't ask that question. I'll shut up. All right, angular momentum of a rotating body. Simplest possible rotating body you can make is a particle, right? So angular momentum of a particle is a mass on a massless string going like this, roundy, 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 right? The angular momentum would be RmV sine theta, but if you're rotating a string around your head, what's theta? It's the angle between the string and the direction it's going, which is 90 degrees. So it would just be RmV for a thing going around your head. Good? If V is R omega, that means angular momentum would be Rm times R omega, right? Which is mr squared omega, right? What's mr squared?
Moment of inertia.
Of?
A particle.
Particle. So, L equals I omega. Cool? All right. And that's for a particle. Okay, let's keep going. L equals I omega for any rotating object. Now, once again, what's the law of conservation of momentum state?
The total momentum.
Total momentum at every point in time is the same, right? Which means total momentum is constant. Does it hold true for angular momentum? Sure. Okay, if we're so sure about that, if I told you I'm going to run this hovercraft in front of you and your heads are going to turn, watch. Was the angular momentum from James's point of view, was the angular momentum the same at every point in time?
No.
Who says that the angular momentum with respect to James's head was the same when it was here versus when it was here? Raise your hand. Who says it was different? Who says it changed?
Let's see.
Yeah, always say
This is kind of binary. Say it was the same or it was not the same.
Oh, so it's always the same.
What do you think? Does anyone think it was not the same here versus here?
It's.
How can it possibly be the same? Because his head was going faster. Yes! You're right. Yeah, I know. You get everything right in advance. I know.
He's like dying. He's like, I said that 10 minutes ago.
No, you're totally right, though. Absolutely, totally, 100% perfect. The angular velocity gets faster as you get closer, but R gets smaller. And wait, sine theta, what happens to sine theta? Got bigger too, right. So everything, all those three factors all kind of balance out. So if you look at it this way, in the absence of an external torque, the angular momentum of the system is always constant. So here it is for a moving particle. All right? Angular momentum at point 1 versus point 2 versus point 3 versus point 4 versus point 5. M is constant, right? V is constant. And R1 sine theta 1 equals R2 sine theta 2. How come?
Because radius goes
Because R is the distance from the vertical distance from the axis to the path of travel, right? That's R sine theta. Big R is little r sine theta. This distance is always constant. So R sine theta is constant the whole time. Does that make sense? As a result, the angular momentum is constant along that path just as long as you don't bump the puck. Or the puck doesn't slow down because of friction or something else happens. Does that make sense? All right, cool. Now, we've established that there's such a thing as angular velocity for a particle. We've established that there's such a thing as angular momentum for a particle and for solid objects. Is there an angular version of Newton's second law?
Yeah.
Of course. What is it? Say- Net torque equals I alpha, right? But remember way back when I mentioned there's actually an even cooler version of Newton's second law that has to do with momentum?
Yes.
Net torque equals something to do with the momentum, right? It was dp over dt.
Yeah.
Is the rate of change of momentum. Torque is the rate of change of momentum. What's the angular version of that? dl over dt. I just said torque over and over again. I meant force. Sorry. Yes, torque. Force is dp over dt. Net torque would be dl over dt. So here it is. And the angular impulse momentum theorem. What was the impulse momentum theorem originally?
Change of momentum equals force times time.
Wow, that was a way too difficult way of saying impulse changes momentum. That's the impulse momentum theorem, right? If you have an impulse, you're going to change your momentum. Okay. What's the angular version of that?
Angular impulse.
Angular impulse changes
Angular.
angular momentum. Good. What's an angular impulse?
Change it toward times
Well, what's a regular impulse?
force times time.
Force times time. So what's an angular impulse?
Torque times time.
Torque times time. Or if the torque is changing, it would be integral of torque dt. Good? Would give you a change in L. All right, fine. These two are actually the same statement. I don't know if you notice. This one right here and this one right here are the same thing. Did you guys know that?
Yeah.
Newton's second law and the impulse momentum theorem are actually the same thing. One's just expressed as an integral and the other one's expressed as a derivative.
Yeah, because some is the
Yeah, it's the exact same thing other than that. All right. Conservation of angular momentum problem types. Okay, so conservation of momentum was like two things colliding, right? Conservation of angular momentum, well, is still two things colliding. But here's the goofy part. If two particles collide, do both particles have angular momentum? Yes, they do. So if you have a particle hitting a particle as a 2D collision, you could do that as an angular momentum problem rather than as a linear momentum problem. All right. Another one would be particle-particle explosion. Blows apart. You could do that as an angular momentum problem if you wanted to. Just pick an axis of rotation and solve all the angular momentums instead of the linear moments. I don't know why you would want to do that because it typically makes the problem harder, but you could do it. Particle body collision. True story. Well, actually, no. Let's just do a really quick demo. What is the angular momentum of that door right now?
0.
0. Now, if I were to throw this ball at that door, would the ball have angular momentum?
With respect.
Let's try it. Wow, that didn't do anything. Oh, no, it did! It did!
Just roll the bowling ball.
After the collision, did the door have angular momentum?
Yeah.
Yes. Before the collision, did the door have angular momentum?
No.
No. So where did the angular momentum of the door come from?
The ball.
The ball had to have had angular momentum if angular momentum is conserved. Right? Had to have. How did this ball have angular momentum?
It was moving with respect to the axis of the door.
It was moving respect to the axis of the door because when it was coming at it, right, it was like, whoa, and then from the point of view of the door, it was like the door was looking at it, and it hit there and collided, and then the door had some angular momentum. Got it?
Yeah.
Yeah.
All right. Did I ever tell you my true story about this?
No.
Okay, yeah, I was probably gone in the hospital when I would have had the chance before. So the question was, it was actually a momentum question. But it went like this. This is actually a true story. It's about 3 years ago. My wife and I were going to meet a friend downtown on Devon Avenue. And raise your hand if you've ever been to Devon Avenue.
I haven't found Avenue in my neighborhood.
Wait, no, you have a long one, right? That goes.
Do you guys know like what Devon Avenue is famous for?
It starts on one side, I see the goal on the side.
It's like all the awesome Indian restaurants.
Oh, really?
Yes.
So you're trying to say that these two aren't raising their hands?
It's really tons of great restaurants, tons of good food, tons of great shops, great place to go. So we were gonna go out for Indian food on Devon Avenue, and we got down there, and usually on like Friday, Saturday, it's packed. It's like you can't get street parking because it's super popular. So we got down there, and we actually got really lucky because we got to like right where the restaurant was. We took a left on one of the side streets, and we found a parking spot like right away, like within 1 block of Devon Avenue, which we were very excited about. So we got out of the car. My wife got out of the right side. I got out of the left side. I was driving. Got out of the car, and we were going to walk across the street. So we walked across the street. It was a really narrow street. And then we were going to walk down to where the restaurant was on that block. And so we got out of the car. We looked back, and I realized I'd left the driver's side car door open. And I freaked out because there's actually another car coming. And it was a narrow street, and they were like going to hit the door if I didn't do something. Fortunately, I had 2 things in my pocket. I had a lump of clay, and I had a Super Ball. And they were like about this big. They're the same size.
I'll take things that didn't happen for $1,000.
This is just totally true story. And so,
If it's true, you have to tell us where the lump of clay came from. Why
Yeah.
is it in your pocket?
I don't know, don't you keep lumps of clay in your pocket? And so,
Not even like a clay thing, just a lump of clay.
so the question is, the car is barreling towards the open door and is gonna like rip the door off. Which do I throw? Because I only have time to throw one.
Wait, to see what
Lump of
clay.
clay. It's heavier.
The super ball or the lump of clay?
The ball. The super.
If you
The
can
lump
aim
of
it at a
clay
car,
because it's
What are the
more
clay
likely to
oh wait,
The bounce
give
like
all of
Super ball
its
because it'll have
angular
more
momentum to the door.
No, because the lump of clay
The
was
ball is
attached
saying
to the
it's
door.
super
The
ball
lump of clay
because
was
it will
attached to the
outlast
door.
force
Okay.
times.
So let's have a vote. Let's have a vote. Who says throw the lump of clay?
The clay will stick to the door, guys.
That
Okay,
was
clay
the
will
first-
stick to the door. I agree.
Yeah, but what's the formula for it?
Okay, hands down.
The force times time is time equals forever.
We're having
Who
a-
says throw the super ball?
Exactly.
Wow, it's like 50-50 split.
That's the thing.
What's the right answer?
Because you asked it second.
Super ball, why?
The time that it's acting the force is much smaller.
Oh.
Because
So that-
Because when it bounces off, it doesn't.
Well, we could attempt to answer this in terms of angular momentum, or we could attempt to answer it in terms of linear momentum, and the answer should be the same, right? Because physics shouldn't care which way you analyze it. So, which way do you want to go? Linear or angular? Angular. Okay, we'll do angular. So the question is, they both have a mass of 1 kilogram. They're both traveling at 20 meters a second this way. So before they get to the door, what's the angular momentum of the door? 0. What's the angular momentum of the ball? RMV sine theta, right? With respect to that. So, but it's the same either way, whether it's clay or super ball, as long as m is the same, which it is. Okay, fine. The ball bounces back. The clay doesn't. Agree?
Yeah.
So what is the total change in momentum of the super ball? 2 RMV sine theta, because it's going this way, now it's coming back the other way with the same speed, right? 2 RMV sine theta. What's the total change in momentum of the clay? Just RMV sine theta. So which one gives you a bigger change in momentum? The bouncing does. Got it? Because it's going this way with a v that way. It's a change in velocity of 2v.
Okay, but then what's the difference between RMV sin theta, 2 RMV sin theta
Minus 0?
The initial angular momentum would be RMV sin theta.
And the final RMV, the final would be negative RMV sine theta for a total change of 2 RMV sine theta. So the bigger momentum change occurs for the super ball versus the lump of clay.